Consider the following graphs, which all have vertical asymptotes. As we approach one of these vertical asymptotes, the function does not approach any specific limit value L, but it's still behaving in a predictable way. We can express this behavior with these infinite limit statements. The book says that a limit is infinity if the function is positive and grows arbitrarily large as x approaches c. For minus infinity, they just say the function is negative and grows arbitrarily large as x approaches c. And we define these analogously for the one-sided limits. So what infinite limit statements can you make about each of these three graphs? Pause the video and think about your answer. For the first graph, y equals 1 over x squared, the two-sided limit as x goes to 0 is simply positive infinity. For 1 over x plus 4, as we approach negative 4 from the left, the function goes down to minus infinity, and as we approach it on the right, the function goes to plus infinity. Why is this? When x is a little less than negative 4, this denominator is negative. So we're getting 1 over a tiny negative thing. That makes a giant negative thing. Similarly, on the right, x plus 4 is going to be positive, and when you divide 1 by a tiny positive thing, you get a giant positive number. So the reason it's different for 1 over x squared, the reason we have a two-sided limit there, is that regardless of what x is, whether it's positive or negative, x squared is positive. So we're always dividing 1 by a tiny positive thing, and we get a giant positive answer. The limit as x goes to 0 from the right is minus infinity. There are several subtle points here about the natural log graph. First of all, why are we getting negative infinity here? It's harder to logic it out than for the other two functions because we intuitively understand division better than taking a log. That's why it's so important to spend time reviewing that pre-calculus material. So here when we say the natural log of a tiny number is a giant negative number, that's really about exponentiation. Raising e to a big negative number makes a tiny positive number. Another subtlety here is that the definition for a limit to be minus infinity says the function should be negative. But we see here the natural log of x is positive for a while, and then it becomes negative. What this really means is that fx is negative when x is sufficiently close to c. Same thing with the positive limit. X should be positive when x is sufficiently close to c. And the last subtlety here is what happens with the limit as x goes to 0 from the left. The function ln x does not exist for negative x values, so we can't take a limit from the left. Now let's think about the question, what does the graph of y equals e to the 1 over x look like? Pause the video and think about this. Try to graph this function in as much detail as you can. Let's start out by thinking about what's happening on the right side of this graph. What's happening when x is positive and when we approach 0 from the right. Well, when x is positive, we're raising e to a positive number. As that positive number gets tinier, 1 over x is getting gigantic, so we're raising e to bigger and bigger power. And that's going to make the whole function bigger and bigger. What about on the left side? When x is negative, we're raising e to a negative power. And as that negative power gets tinier and tinier, 1 over x is still negative, but it's getting to be gigantic. So what's e to a giant negative number? E to a giant negative number is tiny, so this limit is 0. So the graph roughly looks like this. There's actually a horizontal asymptote of y equals 1 on both sides, and we'll see why that is in section 2.7. Also, on the left side of the graph, we don't really have this simple arch shape here. In truth, there's a little dip near x equals 0 on the left. And we'll see why that is in section 4.6 when we talk about graphing in more generality, and we use lots of new sources of information about the graph regarding derivatives. Please go on to the next video, where we'll learn a simple algebraic way to evaluate many limits.